spring break. Next week will be spring break. And so as soon as we come back from spring break, the steps, second distribution, I'm looking for inverse norm, the reverse of normal distribution, normal CDF. So I am using number 3, that's inverse norm. And my calculator is asking me what is the area to the left? What is the percentile? The percentile is 0.359. So that is the area given to me. So that area, the number given to me is 0.3594. So that is the percentile, 35.94%, 0.3594. Okay, and then I'm told to find, my calculator is asking me for the mean, but the mean is 0. Mean of a standard normal is 0. The standard deviation is 1. And now I'm going to calculate what is the z-value. What is the z-value corresponding to area 0.3594? If I hit enter, it's asking me, is that what you want to calculate? Yes, I want to calculate the percentile or the z-score corresponding to 0.3594. When I hit enter, I have negative 0.36. So the z-score corresponding to this is negative. Of course we know it's going to be negative because it's on the left-hand side of the mean. So we know that z is equal to negative 0.36. Negative 0.36. I can use 0.36. The same thing happens here. If I'm told to find P20, it means the 20th percentile. P20 means 20th percentile, the same way I did the other one. And the 20th percentile is area to the left, 20% or 20th percentile. So I'll draw a normal curve, represent 20% of the normal curve on the left. This is the same as 0.2. I will shade the area, and I'm looking for the z-score corresponding to the beginning. The z-score corresponding to the beginning. And then when I'm looking for this, I am reading to the left. The same thing my calculator does. So remember, to find it from your calculator, you do inverse norm. Inverse norm. So second distribution, or second verse, select number 3, and then 0.2, that is 20%. The mean is 0, standard deviation is 1, and I'm going to paste. Okay, and that area is negative. The z-score corresponding to the z-score corresponding to the 20th percentile is negative 0.84. Remember that this is z-score. This is z-score. So negative 0.84, because area cannot be negative. So that is not area. So negative 0.84. All right. So the same thing, even though that these are diagrams from number 7, is asking us the same thing. Asking us the same thing. Find the z-score that corresponds to 0.2776. So you just write inverse norm. Area to the left in decimal is 0.2776. Mean is 0, standard deviation is 1. So put it in your calculator like that. Put it in your calculator, area under the normal curve, uh, 0.2776. Calculate. You go to second distribution. Number 3. And then the question is, find the z-score corresponding to 0.2776, so 0.2776. And then the mean of a normal distribution is 0, standard deviation is 1. And then you can paste. Okay, so the mean is 0, standard deviation is 1. You calculate, and then the z-score. I want to remind you again that we are looking for z-score. And so that is why some answers are negative, because the z-score is on the left-hand side of the mean. If it's on the right-hand side, then it is going to be positive. Okay, so you are going to read the notes also. Remember that you can read the chart. You can also read the chart. So suppose I'm going to read the chart. I can actually, let's get so this is 7.1 notes. 7.1 notes is in your, okay. Yeah, okay, let's get 7.2 notes. Okay, application of normal distribution. Find and interpret the area under the normal curve. Find the value of the normal random from a random variable. So if you're given, you remember we also found the z-score. So calculate instructions for doing both of these. Found in pages. Okay, we're not looking for the pages. So here I can be told to find the area between -1 and 1. I can use the chart. I can be told to find the area between mean equal to 0 and mean is equal to the z-score equal to 1. So actually you'll be given the chart. So I should be able to read the chart. You'll be given the chart. If I'm told to read the chart 0.9082, okay, so let's read this one. So that, let's read this chart. Let's read this one from the chart. Suppose I am told to find the area under the normal curve. Z is less than 1.33. So this is 1.3 here. And then 1.33 is 0.0 here, 0.1, 0.2, 0.3. Therefore, the number corresponding to 1.33 is 0.9082. The number corresponding to 1.33 is 0.9082. Okay. Okay, and then you could be told to find the z value. So when you're given z value, you find the area. When you're given the area, you find the z value. If you're looking for z value, you use area to find it. If you're finding if you're given the area, you find the z value. Okay. Remember that any question on normal distribution, you need to share. You need to share the area. Okay, so the next thing we're going to do is actually get 8.1 and look at it. So what is our 8.1 saying? Corresponding to this value. This is 0.89. Okay, So what I'm going to do is get my calculator as usual. Get my calculator. Turn it on. And I'm going to clear what is in the screen. And then second distribution. And I have inverse norm. It's inverse norm because I'm given the area. I'm given the area and I'm told to find the z value. So 0.89. And now the mean of a normal distribution is 0, standard deviation is 1. So I will paste. And it's asking me, is that what you need? Do you want to find the z-score corresponding to 89th percentile? Because that's what it means. The z-score corresponding to 89th percentile is, okay, therefore that z value is 1.22 to 4 decimal places is 1.2265. 1.2265. 1.2265. See, it is not negative. It is not supposed to be negative because this value, the 89th percentile, is on the right-hand side of the mean. Therefore, it is not negative. The 89th percentile is on the right-hand side of the mean. Okay. So the next one we are going to do is, suppose we are told to do it by hand, actually by chart, so I can read the chart. So I'm going to pull up the chart so I can read the chart. I'm going to pull up the chart. So I want to find that area using a chart. I'm not using calculator this time. I'm using the normal distribution chart. Remember, I'm doing Z, so I am going to the Z chart. This first one here is Z chart. This is not a Z chart, this is T chart. So I am going down to CZ chart. That is Z chart here. And then I'm going to increase it. Remember that what I'm looking for is looking for Z chart corresponding to 0.89. Okay, the Z value corresponding to 0.89. So I want us to see here. I'm going to get so looking for that Z corresponding to 1.89 or 0.89. So right here I see that, okay, so 0.89, 0.89. If I look at 1.2, I will see that this is approximately 0.89 right here. And so I will draw a line on the left, a line on the left to meet that 0.89, and also draw a line from the right, the intersection of the two lines. The intersection of the two lines is see, I have got the number 0.89 approximately. Therefore, the Z value is 1.2. So we'll just look at it. 0, 1, 2, 3. 1.23. Approximately 1.23 is the Z value. 1.23 is the Z value. Okay. So this is our practice test 3. This is our practice test 3. Okay, and so in this unit 3, we will have questions on discrete probability distribution. We have questions on binomial distribution. We have questions on normal distribution. Okay, So we will also be told to find, look at number 4, determine the area under the standard normal curve. So this time we are told to find the area. Find the area under the standard normal curve when Z is, remember this question says area to the left. If it says area to the left, it means you have to find the area to the left. If it says area to the left, see, all of them are area to the left in this number 4. And all you need to do is use your, okay, when the question says area to the left, you already know that you have to draw a normal curve, area to the left. Okay, and the question says starting from 0.39. 0.39 is positive, so somewhere here, and it says area to the left. So what it means, at this point I have negative 1/8 to the power 99, and the Z value here is 0.39. Okay, so what I have to do is, remember we did this before, we are actually going over what we have done because it's in unit 3. So normal CDF, normal cumulative density function, the lower bound is negative infinity, negative 1/8 to the power 99. The upper bound is 0.39. The mean is 0, standard deviation is 1. So you get your calculator. So get your calculator and put in the data that from the way you have it in have it on the board. So second distribution, this time is area. I'm looking for the value of the area. I'm looking for the area, so I'll use normal CDF. When I'm looking for the area, I use normal CDF. When I'm looking for Z value, I will use inverse norm. So number 2, normal CDF, because I'm looking for the area. The lower bound is negative infinity. The upper bound is 0.39. And the mean is 0, standard deviation is 1. Okay. And then we hit enter. Therefore, the area under the normal curve to the left of 0.39 is 65.17%. You see, 65 is greater than 0.5. That means that this area started from the right-hand side of the mean. The area started from the right-hand side of the mean. So I'm going to pull up 8.1 notes. 8.1 notes. Okay, so we can read it and find out what it is saying. What is 8.1 note saying? Okay. All right, so this is 8.1. 8.1. And today is 3/11/25. Okay, what are the learning objectives? You should be able to describe the distribution of sample means when it's a normal population, distribution of sample means when it's a non-normal population. So we have to be very careful to know when it is normal. The sample size is greater than 30. Population standard deviation is known. When it's a normal population. When it's a non-normal population, the sample size is less than 30. The population standard deviation is unknown. Unknown. The two data are taken from a simple random sample. So if the If the sample size is less than 30 and the population standard deviation is not known, we say it's a non-normal population. And if it's a non-normal population, we shall use T distribution. T distribution. If it is a normal population, we shall use, if it's a normal population, then we shall use Z distribution. Okay, so I am starting this on time so that we need the whole of next class to do it. Okay, so we call it sampling distribution also. The sampling distribution of the mean, or you can also call it central limit theorem. Central limit theorem. So this section is the central limit theorem or the sampling distribution. You can call it sampling distribution or call it okay. All right, so this is just the notes on this section. So the first one is to read the notes. Read the notes first before you start reading the PowerPoint. All right. The weight of pennies after 1982 are approximately normally distributed with the mean of 2.46 and the standard deviation of this. Approximate the sampling distribution of the mean, sample mean, by obtaining 200 simple random samples. So 200 simple random samples, that is sample mean. And then in the big sample mean, sample size is this. The data on the following slide represents a sample mean of 200, okay, with a simple random sample. So they took a small sample from that. For example, the first sample is 5, had the following this, and has the mean. That means no matter how small the sample is, provided it's greater than 2, you can take small samples from a big sample. Anyway, the important thing is that the central limit theory says, this is the key, this is the cream of central limit theorem. The central limit theorem, CLT, says that no matter how the original data is, even if the original data is skewed right, or the original data is normally distributed, or the original data is skewed left, if you get small samples from here called A, or small samples from B here called B, or small samples from here called C, the density curve you will make from those small samples are going to be normally distributed. So let's say that after getting those small samples, I made a density curve or drew a histogram. When I draw that histogram, the histogram will be bell-shaped. The histogram of the mean of means must be normally distributed or bell-shaped. The histogram of the mean of means or the histogram of the normally will be normally distributed. Even if I got it from A, which is skewed right, or I got it from B, which is normally distributed, or I got it from C, which is skewed left. That is what the central limit theorem said. And it's also said that if I'm going to clean a little bit of this so that I can demonstrate what I was trying to say here. All right. So now the density curve of a central limit theorem must be normally distributed. The density curve of any mean of means or central limit theorem must be normally distributed. where the mean of the density curve, we call it mu x bar, is equal to the mean of the original data, mean of the random variable. Notice the difference between this. This is mu x bar. Why? Because this is the distribution of means. So the mean of the distribution of means is equal to the mean of the original data. Okay. The mean of the distribution of means. In this case, let's look at this question again. In this case, the mean is the mean of the original data. Let's see what it is. Let's see what that mean is. Okay. Did they give us the mean? Okay. So the mean of the original data, according to what they gave us here, is 2.46. 2.46. So the mean here will be 2.46. And the mean here will be 2.46 also. They are equal, despite the fact that this is central limit theorem. The mean of the central limit theorem data are equal. The standard deviation of the central limit theorem, which is standard deviation x bar, you can rewrite it this way. It's called standard error. So it's the same as the standard deviation of the original data divided by square root of sample size. The standard deviation of the mean of means or the central limit theorem is called the standard error. Same as standard deviation of the original data divided by square root. Okay. And then the mean z-score of the original data is x minus mean over standard deviation. Okay, but the z-score of central limit theorem, the z-score of central limit theorem is actually zx bar is equal to x bar minus mean of the central limit theorem all over standard error. Standard error is the standard deviation of the central limit theorem. So this is for z-score of central limit theorem. This is the formula for z-score of central limit theorem. Formula for we will solve many problems on central limit theorem, so that make sure I clear the confusion. So this is where they demonstrated it. They found 200 samples and found the mean of each sample. And when you finish, the mean of the distribution of means here will be approximately equal to the mean of the original data. The mean of the distribution of means will be approximately equal to the mean of the original data. Okay, so the mean of 200 is equal to that. So we no matter how, it doesn't really matter whether it is skewed right or skewed left or normally distributed, the mean of the central limit theorem is the mean of central limit theorem is equal to the mean of the original data. But the standard deviation of central limit theorem, standard error, is equal to standard deviation of the original data divided by square root of sample size. We will be doing an example, an easier example that will show us, okay, what this all this means. Okay, so that's what we just said. That's what I just emphasized. And then we shall get to a practice test, get into practice and solve problems on central limit theorem. Okay, so this is the notes. So if you like, you can read the notes first, then read the notes, then also read the PowerPoint, watch the video, and then start doing your, especially in this section 8.1. Okay, so we are going to practice tests. So we can practice questions on central limit theorem. So we are working on questions on central limit theorem. Last section for Unit 3. This is the last section for Unit 3. Okay, so so let's get a question. All right, number 8 is an example. Number 8 is, let me see, yeah, number 8. Number 8 is a question for a reason. I'm actually going to copy it on a whiteboard. It's a simple question, but I want to copy it on a whiteboard. All right, so determine the mu x bar. The question is asking us to find the mu x bar, the mean of the central limit theorem. Whenever you see from now on, whenever you see mu x bar is the mean of the central limit theorem. So we are told to find it, determine mu x bar. All right, so that's what we are going to find now. Okay. So I'm getting, let me get this, let me clear this out. Okay. Okay, so mu x bar is what I am asked to find. I am also told to find the standard error. Standard error is the standard deviation of central limit theorem. But what am I given? What am I given? This is question number 1. This is question number 2. But what am I given? I am given that the mean of the original data is 65. I am also given that the standard deviation of the original data is 5. And I am given that the sample size is 23. Okay. So now I'm told to find the mean of the central limit theorem. The mean of the central limit theorem is the same as the mean of the original data. That's what the theorem said. The theorem said that in the mean of the original data is equal to the mean of central limit theorem. Okay, so the mean of the original data is equal, which means mu x bar is 65. So mu x bar is 65. And now, so they gave me the standard deviation of the original data and they gave me the sample size at 23. Therefore, I can now determine the standard error. The standard error is the standard deviation of the original data divided by square root of sample size. And this implies that I will plug in what I'm given. I'll plug in 5 for standard deviation, and I'll plug in 22 for 23 for the sample size. So all I need to do at this point is get my calculator and simplify. When I simplify, I'll get the value of the standard error. Remember, the standard error is the standard deviation of central limit theorem. And the central limit theorem is called the mean of means. The mean of means. Okay, so I'm going to divide 5 divided by square root of 23, and my answer is equal to the standard error. Therefore, the standard error is 1.043. Approximately, standard error is 1.043. Approximately. Standard error is 1.043 approximately. All right, so you see that the standard error is always smaller. You can see that the standard error is always smaller than the standard deviation of the original data. Always. Why? Why is standard error going to be smaller than the standard deviation of the original data? Because we are dividing by a bigger number. We are dividing the deviation of the original data by a bigger number. That is why the standard error is always smaller than the standard deviation of the mean of means. The standard error is always smaller than the standard deviation of the original data. And standard error is called the standard deviation of the mean of means. Mean of means is the same as central limit theorem. And so I don't want to get confused when we start talking about mean of central limit theorem. I mean, they are the same. They are the same anyway. So we need to understand 8.1. We'll come back on Thursday and do it again, and we'll start doing this. Our test will be immediately after spring break. Our test will be immediately after spring break. So everybody needs to, when you're on spring break, you have to study for Unit 3. Okay, so let me know if you have any question. Do you have any question?